So in this video we're going to be talking about second order differential equations, and usually we will have equations of the form a of x times y double prime of x plus b of x y prime x plus c of x y x equals to another function f of x. And this is what we call a linear non-homogeneous second order differential equation. It is non-homogeneous because we have a function of x on the right hand side, and it is a linear second order differential equation with non-constant coefficients because we have other functions of x attached to this. So just to give you an example of what this might look like, we may get something like this: plus sine of x y prime plus 3xy equals to x squared plus 1. So this is an example of the most general case you can have for a linear second order differential equation. But the differential equations we're going to be focusing on today, because we need to learn some techniques for solving simpler cases before we move on to this, is called so the differential equation we're going to solve today is a linear homogeneous second order differential equation with constant coefficients, and we call it homogeneous. So homogeneous because the function f of x on the right hand side is 0. I'm sorry, I forgot the y here. So that's what it should look like. And we have constant coefficients attached to all the derivatives and the function y itself. So what we're going to do with this is we're going to assume a solution of the form some constant k times e to the power of r x. And the reason for that is that exponential functions usually differentiate very nicely because we know that we get the original function again. So let's have y prime equals to rk e to the power of rx, which is the same as saying r times y. And then y double prime is going to be what? It's going to be r squared k e to the power of rx equals to r squared times y. So if we grab all these derivatives and put them back into the original equation here, what are we going to get? Well, we're going to get a times r squared y plus b times ry plus c times y equals to 0. And immediately we notice that the solution y vanishes, it just goes to 0. And then we're going to be left with this equation, which is actually just an equation with constants in it. So br plus c equals to 0. So that's a really interesting thing, because just by doing this procedure, we have come to an equation that is a quadratic equation, and it allows us to find the exact values of r, which is a component, a crucial component of our solution here. So let's see what we can do with this. Using the quadratic formula, we know that the roots of this equation are going to be minus b plus or minus square root of b squared minus 4ac over 2a. So this is going to be our solution, but we need to consider three cases, right? Because we don't know what the relationship between a, b, and c is. So we need to consider three cases. So I'm going to have the first case, which is going to be b squared minus 4ac. Oh, before I move on to that, so one of the things that we need to notice is that the solution should actually be a superposition of both of this, because this is a linear differential equation that we just solved. We should expect a linear superposition of two solutions, one for each of those roots. We need to consider both of them. So let's rewrite the concept as c1 e to the power of r1x plus c2 times e to the power of r2x. So this is going to be our general solution to the differential equation. So if we have this discriminant greater than 0, then that means that r1 is distinct from r2, and they're both real. So they both belong to the real numbers. And then our solution is simply going to be written as c1 e to the r1x plus c2 e to the r2x. In the case that b squared is minus 4ac is equal to 0, we're actually going to have the same roots, because if we make this 0, both roots are going to be the same. So they're both going to be real. But now that means that we're going to have the same solution for both. And because we know that this should be a linear superposition of two distinct solutions, what we need to do is we need to manipulate it in such a way that the two functions are different. So now I'm going to replace R1 and R2 by R, just to make it more general, because they're the same. And now on this side, so one of them has to be different, so we're going to multiply by an x. And then this is going to be equal to that. And you can test this out by differentiating and putting back into the equation and seeing what you get for the roots. And finally, the third case is going to be for when the discriminant is less than 0, so that's a negative number. What happens when you have the square root of a negative number? You get a complex number. So in this case, we're going to have R1 is distinct from R2, and now they're going to belong to the set of complex numbers. So now it's going to get a little bit trickier, because we're going to have the roots equal alpha, which is the real part, plus or minus I beta. And that in turn is going to imply that our equation, so I'm going to have to write this down on the top because I'm running out of room here. So let's go back to the top and let's erase all of this. So for the third case, what we're going to have is the general solution yx equals to e alpha plus I beta, where I is the imaginary number, x plus, and I forgot the c1 here, c2 e to the power of alpha minus I beta x, and we can rewrite this as e to the power of alpha x times c1 e to the power of I beta x plus c2 e to the power of minus I beta x. So this is how we will represent the general solution for the case in which the roots of that equation, which we call the characteristic equation, are complex. So that's one way to write it down, but usually we don't like having complex numbers in our function. So what we're going to do is we're going to do a little algebraic manipulation here. So just to do a recap of complex numbers, this is the Euler identity, which tells us that we can basically represent a complex exponential function as a sum of two trigonometric functions. So we're going to have a real part and a imaginary part. So if we make that substitution here, what are we going to get? We're going to get e to the alpha x. So this is going to be y of x. So this is going to be c1 cosine of beta x plus I c1 sine beta x plus c2 cosine beta x minus I c2 sine beta x. And the reason we have a minus here is because when you have a minus here, you can imagine that the imaginary part is going to become negative. So that's what we have here. So we can make a substitution here. Let's have c1 and c2 equal to another constant a. And let's have c1 minus c2 times the imaginary unit I equal to another constant b. So now that we have that, we're going to have the following expression. So the whole idea was to get rid of those imaginary units in the final general solution. So e to the alpha x times a times cosine of beta x plus b times sine beta x. And this is another way in which we can write that solution, and it is equivalent to this form that I have on the top. So sometimes this might be more convenient if you need to differentiate it, because this is easier to differentiate. But sometimes if you want to graph it, or if you want to work with the solution directly, this might be more convenient. So it's just a matter of choice, really. And we'll show in future videos how to make use of both of them in different scenarios. But for now, this is essentially the three different solutions that you can get for differential equations based on the characteristic equation, which I accidentally erased here. So the characteristic equation is this equation here, where you solve for the roots r, and the three sets of solutions that you can have are going to correspond to the value of the discriminant. So this is for the first one where they're both distinct and real. This one here is for when they're equal and real. And finally, for when the roots are complex and distinct, you're going to have this solution here or this solution here. And in the next video, we're going to solve some examples using the characteristic equation, and we're going to take into consideration all three cases.